Bye, Grace. Okay. Write down, if you don't have this example, write down this example. I'm gonna walk you through the basic steps here, and I think you guys will end up liking it. Some people are better at the math part of this shebang, so you know, whatever floats your boat. I thought I printed this for you. It's called like AP Chemistry, REDOX, Stoichiometry lecture notes. See it? Yay, nay? It's okay if you don't. There's only 3 questions there. And then you guys have your stuff at the phone. Some of us are probably just pulling out the important information, which I prefer. So usually once I see a problem, I don't read the problem more than once. I go straight into analyzing it to the pieces that I need, which is not very much. So what volume? So what's my question? Volume of milliliters of FeSO4, iron 2 sulfate, is needed to completely reduce blah 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 blah. Okay, so this other stuff these are givens. They're information pieces that you need to use in your stoichiometry. So I like to write them down as my givens, my notes. So my givens are 0.200 molar iron 2 sulfate, and I have 50 milliliters of 0.400 molar sodium dichromate. Right, so that's my given information. And notice I like to group together the common things, because those are going to have to be used together, because that's how you cancel units. All right, so whenever you have a stoichiometry problem, it was always the first thing we always had to do. BC. So we always have to have our BC. And then we had to start with what? What you're given, but commonly you're given 3 or 4 things. So what's the most common unit that we can usually get to anything with? Moles. So how do you get to moles from information like this given? N times V gives you moles, right? So commonly for stoichiometry in terms of redox, you're going to be given a molarity and a volume of the same compound, and so you need to go ahead and get to moles from that, and then go to moles of something else that you're desiring to figure out something out about, so that would be the iron 2 sulfate. So your BCE here is going to be hard because we don't know what the products are, but we do up here, or you can have your sheet out and look at your common oxidizing agents, reducing agents. So we have iron 2 sulfate, and we have sodium dichromate. What commonly do you know is going to come from this? Chromium 3+. And then the top one we have to figure out, okay? So our options are sulfate and iron. Think about what is happening here, what's happening in this one. Oxidation or reduction. This is a +6, FYI. Okay, so reduction. It's a common oxidizing agent, but it is reduced itself, yes? Okay, so what do we have to choose for the top? Iron, because why? Because what? Because why? Okay, so this one has to be the one that's oxidized, right? Currently iron is a 2+, so what can it oxidize to? 3+, right? And most likely our metals will go to their highest transition state possible, so they will go to their highest oxidation state. All right, so we have our 2 products. Let's just go ahead and finish out these half reactions, okay? I'm going to erase what I wrote right here so I have some space. Okay, what is not going to be included? Actually, I'm just going to rewrite this. Sulfate here is not included. It's a spectator. I'm going to go ahead and cancel it out. So I'm going to put Fe2+, yields Fe3+. Balance that out with what? 1 electron. Yay, okay. What's the spectator in the second reactant? Sodium. So then dichromate goes to this. This one's a really common one, so I'm just going to fly through balancing this in acid, because it says in acidic solution right there, so we have that acid available. 2, 4, 7 waters, 14 H pluses, plus, what is it, 6 over there? Is that right? Alright, so then how do you balance this, finalizing the balancing? Multiply the top one by 6, and finalize by summing them up. So 6 Fe2+ plus 14 H plus dichromate plus 6 iron 3+ plus 2 2 chromiums plus 7 waters. And I just ignored my electrons because they automatically balanced when I did my balancing act. Okay, so step 1 done. We have a BCE. All right, what was the question? What was the question, by the way? All right, so milliliters of our iron 2 sulfate, and we have to start with our given. So which one do you want to start with? Okay, tell me what I'm writing. I'm going to write that in liters if that's okay, just to start with our easier unit here. 1, 2, 3 liters of that sodium solution and 0.400 moles of sodium dichromate. Oh, gosh, it's so long. Per liter of that solution. Okay, yay. Liters are gone. What do you guys want to do now?
Go from moles of that to moles of just CR2O17.
Okay, so we're going to start isolating the individual ions that are present in our BCE. So per sodium chromate or sodium dichromate, how many dichromates are there? 1. So this is easy. 1 mole of sodium dichromate for every 1 mole of dichromate. Okay, so now it's starting to look like more of our BCE. So I just canceled out moles of sodium dichromate, moles of sodium dichromate. Now I'm in moles of dichromate only. What was the purpose of that? What's my next step? Right, because the only thing we're concerned about are our reactants. We have this. Our question is iron 2 sulfate. Well, that means we have to get to iron 2. And then eventually we'll get to iron 2 sulfate. Okay, so this right here, 6 moles of iron 2 plus and 1 mole of dichromate because of our ratio of 1 to 6. That's why we get the balance first. If not, nobody would have known what the mole ratio is. So our moles of dichromate are gone, stuck with moles of iron 2. Well, we're almost there. What's our next step? We can go ahead and use the molarity. I'm just going to go just one step farther to show that this is equivalent to what the question's asking. There's 1 mole of iron 2 plus and 1 mole of iron 2 sulfate. This is just going back to the original reactant, showing that we've already canceled out the spectators, but this question specifically is asking for iron 2 sulfate, so I'm going to go all the way back to iron 2 sulfate. All right, now I can use my molarity. What was my molarity? 0.200, so that's 0.200 moles of iron 2 sulfate for every 1 liter of that solution. All right. What is 0.05 times 0.4? Do not use your calculator, see if you can do it. Huh? What's 5% of 40? 0.02, thank you. So this is like divided by half. So if this was 0.5 times 0.4, that would be 0.2. Yes? So it's half of 4. But since it's 0.5, you move the decimal back 1 more, so that's 0.02. 0.02 times 1, easy. 0.02 times 6. 0.12. 0.12 divided by 0.2. 0.6. So 12 divided by 2 is 6. So that's the decimal movement. Okay? I didn't touch the calculator, guys. You guys are awesome. Okay, so 600 milliliters of solution, or 0.6 liters. Now, let's see if that actually makes sense, okay? So it's 600 milliliters of that iron 2 sulfate is required. That's a lot. Like, that freaked me out a little bit. I was like, 600, geez Louise. Let's see if it makes sense. So we have a 6-to-1 ratio. So you require 6 times as much iron as you do dichromate, right? All right, and so 6-to-1 would be, let's see, 500 times 6 is, 50 times 6 is 300. However, this is a 0.2 solution, well, this is a 0.4. So you have to double that amount that you need because you have to neutralize like twice the concentration. So 300 times 2, 600. We almost, if we had stopped here, we probably could have done that without all this stoichiometry. Thinking about it. Yeah? Yeah? Okay. Just trying to help the brother out where I can. Okay, this one. This one's a little harder because it's really wordy and it walks you through like 3 processes in one question. A sample of tin ore. Okay, so tin ore. This just means a rock with some tin in it. Okay, it's like from an ore mine. With a mass of 0.3 grams was dissolved in acid solution, so we have some H plus floating around. All the tin was changed from tin, so that's tin, just straight up tin, solid, to tin 2. And this is what I write on my paper. I don't go back and read this over and over again. I write down exactly the information I need. So pretty much, my givens here are so far 3 grams of tin ore. I'm sorry, 0.30 grams of tin ore. I have H plus solution, so it means I know I'm in acid. I have tin solid ore that's been converted to tin 2 plus. Then this solution right here, this solution was then titrated with potassium permanganate. Okay, and that particular solution was 0.0500 molar, and I only used 8.08 milliliters. What's my question? Grams of tin, right? Just straight tin, not tin ore. Alright, so this one's a little harder because we have, the first thing that happened was, okay, we got all the tin to the tin 2. And then we reacted tin 2 with this. So the reaction we're actually talking about is the tin 2 reacting with the permanganate. Because that's what we have information for. We have information about permanganate, so we have to use that. Okay? However, it's in acidic solution because it's just floating around, so we can balance an acid. So I know for sure I'm using permanganate. And what does that commonly go to? Mn2 plus. Now, if we're using tin 2, let's see if that makes sense. Can tin 2 go to anything that is, let's see here. This is a 7 plus, so that is reduced. Can this be oxidized? Yes, it can go to tin 4. Okay, so that's just like you write down your initial products of what you think they could be, and you verify, yep, one's reduced, one's oxidized. All right, let's move on. Yeah.
How do I know like what metals go to? Like how do I know like
There's on the summer assignment, I had a list of common transition metals, but the ones that we know for sure are lead 2 and 4, and then tin and lead are right under each other. Yeah, over each other. So tin can go 2 or 4, chromium can go 3, and some other stuff. Cobalt 2 or 3, copper 1 or 2, zinc 2. You have to memorize them. Sorry. Okay. Balance this. So 4 waters. Is that right? Yeah. Okay. Plus 8 pluses, and 5 electrons. This is like getting annoying because we have to write that one so much. Plus 2 electrons. So balance it by doing what? So times 2 times what? 5. So let's see here. 16 H pluses, 2 MnO4 minuses, 5 SN2 pluses yields 5 SN4 pluses and 2 Mn2 pluses and 8 oxides. Anything cancels? No. Okay. How much tin in grams do we have? That was our question, right? Here's our BCE. All right. What information do we have to start with? I can do what? I can find moles, right, of my KMnO4. So I'm going to take I'm going to do millimoles here, okay? 8.08 milliliters of KMnO4 times 0.0500 moles of KMnO4 per that's millimoles, millimole right there, per milliliter of KMnO4 solution. So now my 8 milliliters of KMnO4, and that's gone. Yay. Now what do you want to do? We did the same thing earlier. Not quite yet. Let's go just to the information that's from our BCE. So what particular ions in our BCE? MnO4. So 1 mole, I'm not writing millimoles, okay. 1 millimole of KMnO4 contains 1 millimole of MnO4. Okay, that's tedious, but we did it. All right, next, now ratio, right? So 2 to 5. I'm trying to get back to 10:2. So 2 millimoles of MnO4 minus on the bottom, 5 millimoles of SN2 plus on top. And then, can we go farther? What's our end game here? Grams. Can we get to grams from this? Yes, we don't have volume to work with, we don't have molarity to work with. That means the only thing we have is moles to grams, and that's our last step here, okay? So I'm going to take this to moles, like true moles. So in one mole of 10(2), there is 1,000 millimoles of 10(2). So I'm just solving this an alternate way for those of you like millis. And I'm not quite able to say this is true 10 yet, but if you had to write the BCE between 10 and 10(2), what would the ratio be between 10 and 10(2)? 1 to 1, right? So this is in the back of your head. You know, I'm going to erase this in a second, 10 to 10(2 plus, which is what occurred in that very original reaction when all the HCl processed the 10 to 10(2). This was a 1 to 1 mole ratio. Okay, so we didn't write that down, but that's because we know most metals are 1 to 1 because they're just losing electrons, and that's it. So I know this is a 1 to 1. So I'm going to write that down. So 1 mole of 10(2) is equivalent to saying 1 mole of 10. And then our final step would be go to grams. So 1 mole of 10 is like 118.7. Yeah, grams. 10. I don't know if you can guesstimate this unit, but you can try if you want. Nope. Brain power is on low in 4th period, I know. All right, so go ahead and somebody tell me. Go for it.
Are we going to have to know millimoles for the APSM?
Millimoles are common in terms of like, they might say we're starting off with 5 millimoles of something, but you can always convert straight to moles out of that. You don't have to work with them if you don't like them. Yeah.
We have millimoles
Because that is the only, I have to eventually get to something that's in my BC, so I had to go from MnO4 to 10(2), according to, that's the only ratio I have.
Why can't we get it?
Because you don't have information about MnO2 plus. We were only given information regarding the KMnO4, so that's what you're starting with. Why waste your time going to MnO2 plus? Because it's not even like a question in the, or something in the question. So you go straight to what's been asked for, which is 10. Yeah.
How did you know that 1 mole of KMnO4 equals 1?
Because this here has a 1 in the back, and this is a 1. I know, it's just something you knew a while ago and you forget. Alright, so did we get like 0.119887 grams of tin?
Yes.
Yeah.
So when you're doing mole ratios, you can
I'm not, that's not my final answer.
So you can take them from the half reactions as well, not just the final BCE.
No, you need your final.
Okay.
Because sometimes it works out in the original, but you always need your final. Okay. Okay, so I'm going to leave this like this for a minute. But if you wanted to write down the correct sig figs, how many would you need? 3. So we would need to round up, right?
Yeah.
So that 8 rounds that 9 up, and then blah, blah, blah. So 0.200 grams of tin. That will be our final. But I'm not going to round right now because I know there's a second part of the question you guys probably haven't seen. What is the percentage of tin in the ore? All right, so what data point have we not seen? What data point have we not used, I mean?
The masses in ore.
All right, so what's up, Nick? Oh, I don't know. That's a 1, 2. I knew there was a 2 in there. Where the 2 goes? 120 grams. You guys agreed with me. Okay, I'm going to take this right here, 0.11988 grams of tin, and I'm going to see how much tin is in my original ore sample in terms of percent, and that would be 40. I got 39.96. I mean, I was going to round. Did you do that one or that one?
That one.
I also did this on my cell phone, so cell phone calculators, worthless.
Well,
Worthless.
You did something.
I know. I know. But that's what I got. Somebody else double check.
that's what I got, but I just did something.
Oh, I thought you said 40 point something something.
Oh,
Not 40.0. Okay.
1.5.
Yeah, that's the answer to our question. These are long.
2 hours later.
These are long because you have to do so much balancing in the beginning, but after that, there's usually multiple questions that regard the same balancing act. Okay, let's do one more. One more, and I'm going to talk you through this one too because it's a little bit wordy. Potassium peroxide disulfate. Remember I told you I knew what S2O8 was? It's peroxide disulfate. Is a powerful oxidizing agent that can oxidize chromium-3 to dichromate. We don't ever see that, right? We always see the opposite. All right, so what's one half reaction?
Oh my god, that
Okay, so that's one half, and we're gonna finish that off. In acidic solutions, peroxide disulfate ions is reduced to sulfate. Guess what? You don't have to predict a darn thing. Yay! It's very abnormal for you not to predict a darn thing, but it's here. Okay, so that is going to be reduced to sulfate. What mass? So question: what mass of potassium peroxide disulfate is required to oxidize the chromium in chromium-3 nitrate? Okay, chromium-3 nitrate. If given 100 mils of 0.020 molar fat.
I know.
No, the chromium-3 nitrate itself technically doesn't matter, but since it's asking for grams, I like to make sure we use the whole thing just in case you ever do have to include that nitrate mass into something. All right, we have our half reactions, not quite. Let's do this. Okay, let's balance these babies. Oh, I'm all backwards now. 7 waters go over here. 14 H pluses. 6 electrons here. Yeah? Yeah. Oh, there's your 2 there, okay. And then this needs a 2. 4, 2. Multipliers are?
You just multiply one by three.
You can just multiply the bottom 1 by 3. So our final answer is 7 waters, 2 chromium 3s, 3 peroxide disulfates, yielding dichromate, 14 H pluses, and 6 sulfates. Okay. Check. Where do you guys want to start now? So start with chromium-3 nitrate because that's your M and V, right? To get to moles of chromium-3 nitrate, then get from moles of chromium-3 nitrate to moles of chromium-3 plus, and then moles of chromium-3 plus to moles of peroxide disulfate with a 2 to 3 ratio. Then moles of peroxide disulfate to moles of potassium peroxide disulfate, which is a what ratio? This has an imaginary 1 behind it, right? So 1 to 1, and then molar mass. Yeah, there's 2 potassiums, so it would be a 2 to 1 for potassium, but it's a 1 to 1 for peroxide disulfate. Yeah. All right, so we just walked through that. Now let's write it. 1000 liters times 0.020 moles of chromium. I'm going fast and furious here, okay? 1 mole of chromium. 3 ratio of
I'm just taking my sweet time.
2 moles of chromium. I lied. I said lied. Okay. 2 moles of chromium 3. 3 moles of peroxide disulfate. I told them I wanted 2 smart boards and they said no. Let's continue. 1 mole of peroxydisulfate and every 1 mole of potassium peroxydisulfate, molar mass. I will tell you the molar mass unless you can add it up in your head.
Oh yeah.
Yeah.
You're funny.
20, what is this number? 207. I mean, no, 270.12. And that is, let's see here, fun time. 0.002 times 3 over 2 is 0.001 times 3. 0.003 times 270 times 270. All right, guys. What if you round this up to 300?
0.9.
About 0.9. With the move the decimal over. So, oh, no, 0.9. Yeah. So I was thinking 0.009 in my head when you said that. So about 0.9, so your answer should be about 0.8 something, since it's less than that? Yeah. Yes. Okay, so I mentioned earlier in this unit that we were starting to practice no calculators, and then I felt really bad because I didn't remind you that on Friday. So I curved your test a little bit, to help with those questions that were math intensive.
What? Dude, what's the oops?
So I did that, yeah.
Was the curve already counted on how?
Everything. This is not a laughing matter. I'm not smiling right now. Okay, because we need to practice. But this test for 3 years, it's been probably one of the lowest grades because it's the first time where you have to do memorization, extra math, different techniques you've never actually really done before, orgo, coordinate, all these little things. And so I usually have a small section on the REDOX test, which is this test, because this test is small. It's like, okay, we know how to balance, we can do stoichiometry, and I know a couple more things. Okay, so I usually have about 10 questions that are worth 1 point each that bounce back to your last test. Okay, so that's what we're going to go over some of these shortly, okay? And then I'm doing you guys a favor. There was a inquiry lab, 2-day lab, Wednesday and Thursday. I'm going to drop that. We'll review the procedure about how we would have done it if we had done it, and some of the concepts there. It takes about 30 minutes max, not like 2 hours. So I'll go over that with you, blah, blah, blah. It's called Beer's Law, and we did a little bit of it in Unit 1, but I want to finish it up. So that gives us some time to go over your test too. Yeah, questions? All right, this answer is 0.810. Potassium, this thing, potassium. So I'm trying to model a little bit more of the math and mental math because I know not everyone's keen on that, but earlier I was going 0.1 times 0.02. Well, that moves the decimal back 1, so that's going to give us 0.002 anytime you multiply by, decimal there. So 0.002 times 3. Well, let's not multiply by 3 yet. Let's see the division by the 2 there. So then 0.002 divided by 2 is 0.001. That times 3 is 0.003, and the 0.03 times about, I'm going to say 300 just to make it easy. So 0.003 times this, you guys can do the math, you can actually work it out, or you can guesstimate. It's about 0.9 because you move your decimal back 3 spaces. So that's about 0.9. This is actually less than 300, so you can round it down to 0.8 something. And most of them on multiple choice, they're far enough apart in your magnitudes and that you can guesstimate. Okay, so it is totally possible. It's just a little hard. All right, good with this? The last 5 on your, I think it's 5. Yeah, 5 on yours. So student problems, you see it on your packet. That is homework tonight. So REDOX problem set, 5 questions. The answers are on the bottom. I think I fixed typos. I'm sorry, I have occasionally typos, so I try to fix them before I print them. All right, now you should have done the pre-lab simulations for the REDOX titration. I'm going to give you guys about 30 minutes to give me a procedure for this. The procedure for this is basically somewhat laid out for you. Let me see if I have more. Oh, let me stop this video.